The objective of this demonstration is to study Newton's law of cooling from real data. And the data is available from the Carolina Knowledge Center. So someday they perform this experiment of studying the cooling of a liquid. So they have taken 250 milliliter in beaker of some liquid, and their desire was to get the data with respect to time, and which is here. Yes, this is the real data. The surrounding was at 25 degrees Celsius. So the liquid was heated. Well, 200 milliliter of water was heated to 72 degrees Celsius. And then with the help of thermometer, with every 10 minutes interval, the cooling was studied. Temperature the temperature of water was noted. So it is here 72, 59 and all that. So water is going to have its own characteristic behavior with respect to cooling, right? So it means there must be a common parameter which governs the cooling of hot water, right? So to extract that one, we will construct the differential equation. So let's first do the data plotting. So I have plotted this data. No, not plotted. I have copied this data here. Time is in minutes, and the temperature is in degrees Celsius. Okay. So this is the temperature. So we know that the temperature is going to settle with time around the surrounding temperature. So important is the initial temperature. So initial temperature with respect to differential equations, this is the initial condition. And the surrounding temperature, this is also going to be the parameter of system. Okay, this is important. So if this is equal to 40, so this temperature drop would be different, right? So water is going to cool from a hot temperature in a characteristic way. So let's define a variable y. This is going to define as T minus EA, right? For all times, I define the value minus the value from this one, right? So this turns out to be 47. So now let's plot it. From the plot, my objective is to get the equation, right? So data points. Select data. Add the series. This is the uh, Carolina Knowledge Center data. X values. Of course, these values should be of independent variable time. So you can choose any interval, 2 minutes, 5 minutes, whatever. And the y values for my variable y, these are the values. So I have got a data. So any model can fit into that one, right? So in the exact Newton's law of cooling, there is an exponential model, e raised to the power kt type model. So therefore I prefer that one. And for that one, I will change this scale to logarithmic. So from the axis options, I can just set the scale to logarithm with the sense that it is going to fall on a straight line. So if we approximate this data as a straight line, so Excel provides this analysis, add a trend line, and I'm looking for not the linear one, I'm looking for the exponential relationship, right? Okay, if we approximate this data with the exponential relationship and display equation on chart, and this is the parameter r squared value, which governs how nice the fit is. So you will learn that one in the course of statistics. So for the time being, let's get to the equation. Okay, so equation is this one. Uh, are we able to see that one correctly? Yes. So it has the shape y equal a naught a e raised to the power kt, right? Y equal to a e raised to the power kt, which means there is at the beginning there is the uh, a linear differential equation. So I can set that one in the trend line, because if I set x equal to 0, so the first value of y is 53. In my case, the first value is 47. So I can do that minor adjustment. So how to do that one? Okay, form a trend line. So can I set that equal to exactly 50, 47? Set the intercept. Okay, set the intercept not to 1, and let me set that one at 47, something controlled by my initial condition. Wow. So 47 e raised to the power 0.033x. Now with this parameter k, I can study any type of cooling of water by, say, heating to 80 degrees Celsius and keeping the surrounding temperature somewhere else, right? And how that is going to appear? Let's see that one. So with that one, now the experiment. So for example, if you want to study the temperature, uh, time time 0 and the temperature of water, say, at any value 80, and with the surrounding temperature, we got the equation from our data as y equals 47 times e raised to the power um, minus 0.033x. And if we transform it back to the original variables, then it is T minus TA, which is the surrounding temperature, and equals T naught minus TA, 47, can be transformed to T naught minus TA. That's the original way we have came up with the come up with the number 47 and e raised to the power minus 0.003x. So this number is the characteristic of water. The rest of the parameters are of the system, that the temperature we started with, so which is the initial point, temperature at the time t equal to 0. So here the x represents the time. So for any system of water and its surrounding, we can have now this T temperature variation equation. So that is going to work. So for example, if we start with T equal to 0 and temperature was 80 with the surrounding temperature say 40, so we can have with any step size, say for 5, step size 5. So we can write T as equal to TA, which is the initial condition. So K dollar 3, this value. No, TA is $3. This is the surrounding temperature plus TA, T naught, which is K$3, the value initial temperature minus again $3, 40 value times e raised to the power minus 0.033 times the current time value. So this will be the temperature value, and it will prevail for the the equation would work for any time, and it will move on till the temperature is equal to the surrounding temperature. So it will move on till the temperature becomes 40, which is the temperature of surrounding. So that's the way. And if it is 25, for example, so the values would automatically be updated. And if we look at the curve of the variables, so that will only be seem to that will seem to governed by the parameter k. So I add a new series for x values. X values here are the time, and y values are the temperature values from any starting point. So this is the situation. It is going to vary, and and if I change this graph to the logarithmic scale, so we will be able to observe a straight line, something close to straight line, and that's it. And if I change the other parameters, for example, this one as say 100, so the starting point would be different. However, the trend would remain the same. So if I change that one to different value, so the curve is going to be um, only controlled by the parameter k. So this is fine. However, to look into the process in a more detailed way, and so that it would govern the cooling of any kind of liquid, so we have to develop a mathematical model for it. And the mathematical model essentially means writing the equations in terms of a differential equation. So governing the rates of change. So we have the equation y equals 47 times the e raised to the power minus 0.033x. So let's take here the text x is the time t, and this is 0.033. 0.033. So I take the derivative. So dy dt equals 47 times the e raised to the power minus 0.033t times the constant multiplied to t. And then this factor is the same y. So we have got a linear differential equation. So if we transform it to original variable T minus TA, the temperature difference between uh, water, hot liquid, and the surrounding. So we have at any time, it is y variable. So y as a function of T, and here we have only temperature as a function of T. So we can simplify the original equation and we come across this differential equation in the temperature of liquid, which is dropping from a high temperature T naught, and it is equal to this one, 0.033 times T minus TA. And then to generalize it for any liquid, we can write that the only governing parameter is K. So for this differential equation, if we solve it by separation of variables, so we readily get this equation T minus TA equals A e raised to the power minus KT, with the initial condition T equal to 0 at time equal to 0. The temperature of fluid was at T naught. So A would become T naught minus TA. And then finally, we will get the equation for the process, in which the distinguishing feature for temperatures, the temperature drop in a liquid is the K parameter that has to be related with the physical property of liquid. So this is the story of Newton's law of cooling, from observing the drop of temperature from a high temperature in time. So with the data, we collect the data, and then we develop the uh, graph, and the graph tend to be a straight line on a semi-log paper. And for semi-log paper, to remind ourselves, there are unequal divisions, and the major divisions run in multiples of 10. So this is the linkage between the experimental data to equation, and then the equation in the original variable, and then how do we come across the mathematical model. So the differential equation for Newton's law of cooling is dt divided by dt for time equal to minus k times T minus TA.